Well, thank you for coming. Today, our lecture is about the manipulation of the crop environment, and that includes the use of windbreaks and the different forms that we have for temperature manipulation of the soil or the crops. This lecture is based on chapter 28 of the book, and I encourage you to have a look at it. Let's start with windbreaks. Windbreak is any structure designed to reduce wind speed. Principle is any type of wall more or less permeable. Sometimes we talk about shelter belts as a specific case of windbreaks where we put several rows of trees and shrubs. We have also a specific case of windbreaks that are the scatter windbreaks, that is the association of a crop with protective trees, the so-called agroforestry system. So we have many possibilities for producing windbreaks structures to reduce wind speed and sometimes to change wind direction. Windbreaks are used in many areas, in special those which have permanent winds, like in the Rhone Valley, southern Andalusia, the area of Cádiz, the Great Plains of the USA. Here you see a global map showing with red and darker colors those areas with higher wind speed. We see South America, Argentina and Chile. We see Greenland. This area are the Great Plains of the North America, Western Africa, Mauritania, Sahara, Eastern Africa from here, and parts of the northern India and southern China. There you would find the Himalayas. We have also high wind speeds in northwestern Europe, Norway, United Kingdom. Here you see an aerial view of an agricultural area in the Vallée du Rhône, La Sauvageon, and you can see these parallel structures are specifically windbreaks, like here or here or here, that they are being used, or here, they are being used to protect the crops. One of the worst effects of winds has been the soil erosion, the aeolic soil erosion, and that causes dust storms as the one shown in this picture in Texas in 1935, during the so-called Dust Bowl period. This was the result of intensive agricultural use of the Great Plains that were before covered by grassland, and when they were converted to crops with intensive tillage, that created a huge loss of soil associated with winds. The effects of wind on crops are various. First of all, when plants are subjected to mechanical stress, like that created by wind, there is a reduction in the growth of the aerial part, and there is an increase in the plant mechanical resistance. The plants get shorter with thicker stems, and the root growth is enhanced. This effect is called thigmomorphogenesis. In general, the effect of mechanical stimuli on the growth of plants. by becoming shorter with thicker stems and the increased root growth, that increases the plant mechanical resistance to bending. Sometimes wind provokes mechanical damage on leaves of fruits or stems. Sometimes it creates stem or root lodging. We will see a picture later. And when crops are well watered, high wind means higher evaporation. Sometimes, especially in dryland cereals, dry and hot winds can cause the end of grain filling in cereals, the so-called grain shriveling. Wind can also cause salinization in coastal areas associated with wind drift. Wind also affects the variation of surface temperature. The more wind you have, the less the difference between air temperature and crop temperature. Sometimes, heavy wind may cause the drop of fruits before harvest. Here you see root lodging of a corn crop caused by heavy winds. And here you can see root lodging of grapevines. The plants have fallen on top of the soil. As I said, heavy winds can also cause the drop of fruits before harvest, and these fruits will eventually be lost. Here you see wind damage by the breaking of branches of trees, and you also see fruit drop below the tree. This is fruit drop caused by wind in olive trees, and this is branch breaking by wind also in olive trees. Windbreaks can be made with different elements. Many times we use plants. We can use shrubs, trees, or annual species, or we can use inert structures like hurdles, plastic mesh enclosures, or even solid walls. In the case of plants, it is very common to use conifers like cypress, the genus Cupressus, a spruce of the genus Picea, or pines of the genus Pinus. When we use plants, we have a competition between the windbreak and the crop for space and resources, namely radiation and water. That level of competition will depend on the root distribution. If the trees have a very deep root distribution, the competition with the crop will be milder. In general, we consider that shelter belts, in other words, several rows of trees and shrubs, are better for wildlife, for protecting animals and improving the life of the wildlife. Okay, let's see how the presence of a windbreak affects the environmental conditions in the protected area, in the sheltered zone. We define effectiveness as the length of or the space where wind is reduced, and it is measured as the number of heights of the windbreak where U is reduced. In other words, if you have a windbreak of 10 meters height and it protects across 100 meters, the number of heights is 10. The effectiveness is 10. The effectiveness depends on the width of the windbreak, on the height of the windbreak, and on its porosity. The porosity is the fraction of open space within the windbreak. But the effectiveness also depends on other environmental conditions. For instance, it is proportional to wind speed. So the more wind speed, the higher the effectiveness. The effectiveness is also higher for unstable conditions, in other words, during the daytime, and is less effective during the nighttime. The effectiveness is also maximum when wind is normal to the barrier, and minimum when wind is parallel to the barrier, to the windbreak. But even then, the presence of a windbreak affects wind speed. Medium porosity is the most effective of all porosities. Here we see the effect of the windbreak on wind speed upward. This is the direction of wind flow, and this is the windbreak at point 0. We see that we have some small effect in the direction from the wind, for the wind is coming. But the highest effect, of course, is on the leeward side of the windbreak. We see that the wind speed can be reduced down to less than 30% of wind speed in the open. And that will occur with solid windbreaks, like a wall. If we use instead a conifer, the red line, we see that the effectiveness increases. We have a longer effect of the windbreak. If we have a deciduous, the deciduous is a denser, has less permeability, the deciduous will reduce less, or will have a lower effectiveness as compared to the conifer. But remember, we have even some effect in the windward side of the windbreak. And typically, we have a very strong effect of medium porosity windbreaks, like conifers. We have a strong effect up to 10 to 15 heights of the windbreak, like you can see here. At 15 heights, we have a reduction of more than 30% of wind speed. What is the best orientation for a windbreak? For that, we have to consider what is the prevalent wind direction in our area. And also, we have to consider that, especially in those periods where we require more protection. For instance, to protect farmsteads, any buildings of the farm, and feedlots where we have the cattle, we have to protect from cold winds and blowing snow during winter. So maybe we should orientate our windbreaks normal to the north winds. For field crops, we might be worried about hot, dry winds or from wind-blown soil particles, in special during critical growing periods. For soil erosion control, we have to consider the prevailing winds when the soil is bare, and that happens usually during the winter and early spring. If we want to recharge soil moisture with drifting snow in very cold areas, we should consider the prevailing winter winds. The main criteria for the design of windbreaks is to establish, when we want to cover large areas, we have to establish a set of parallel windbreaks separated a distance between 10 and 15 times their height. So if we use trees with a 10-meter height, we should space those lines of trees at 100 to 150 meters. We will need gaps in the windbreaks to access the fields, but the gaps should be spaced at more than 10 heights. So don't put the gaps closer than that. Consider that gaps in a barrier are funnels that concentrate wind flow. So if we put a lot of holes in the barrier, those will act increasing locally the wind speed, and that might cause important damage to the crop. The main effects of windbreaks on the microclimate of the protected area are related to radiation and temperature and humidity. Of course, the windbreak can intercept part of the radiation, so we will have lower radiation in the shaded areas. Usually, that is not an important effect beyond 1 to 2 heights of the windbreak. The lower effect on radiation is that of north-south oriented windbreaks. Why? Because at noon, when solar radiation is maximum, the shadow cast by the windbreak will be very small. The highest effect of windbreaks on radiation is that of east-west orientation, because we will have always a shaded area to the north part of the windbreak. The presence of the windbreak has also an effect on wind speed and turbulence, and that affects temperature, vapor pressure, evapotranspiration, and wind chill. In the case of temperature, we have a higher soil heating, and that causes a higher air heating during the daytime. And the reason is that when we reduce wind speed, we increase the aerodynamic resistance, and when we increase aerodynamic resistance, the soil will heat more during the daytime. If you wonder why that happens, you can check on chapter 6, that is about soil heating, and that gives you a more complete explanation. If we increase soil temperature during the daytime, that will cause an increase air temperature during the daytime. Then that will be associated, the low wind speed will be associated with a faster soil cooling at night. The temperature inversion will be more extreme, and that increases the risk frost during the night. The reduction in turbulence affects also the vapor pressure. As missing is reduced, we will have more humidity close to the crop. The higher vapor pressure close to the crop, and along with the reduced temperature during the night, will increase the dew deposition at night. So the crop can be wet during longer periods, and that increases the disease risk for aerial diseases. So adding a windbreak, we will have higher temperature during the day, lower temperature at night, and higher humidity and increased dew deposition. The case of evapotranspiration depends on the availability of water for the crop. When we put a windbreak, we are increasing the aerodynamic resistance, and that means lower evapotranspiration when we have enough water for evapotranspiration. But when we have rain-fed crops, at the beginning, the presence of the windbreak improves crop growth, and that means that the evapotranspiration at the start of the season will increase, and that may cause lower available water for terminating the crop cycle. In other words, that means terminal drought and maybe a reduction in yield. But in well-watered crops, we will have equal or higher yields and lower evapotranspiration, which means that windbreaks for irrigated crops might improve the water use efficiency. The reduction in wind speed when we have low temperatures means a reduction in the wind chill. The wind chill is more or less the product of low temperature by wind speed. So by reducing the wind speed, we are reducing the heat losses from livestock, from the wildlife, and from structures. So in the farmstead, we will require less energy for heating the house. We already mentioned that we can have a special case of windbreak, the so-called, that we call scattered windbreaks. That means the presence of trees all over the land, like in the case of the dehesas. The presence of trees on the land will decrease the average wind speed in proportion to the fraction of area covered by the trees. Why? Because the trees will increase the roughness of the land. One important difference between a scattered windbreak and a regular windbreak, where trees are in a row, is that the degree of interaction and the degree of competition too between the tree and the crop is higher when the trees are scattered. We have also an increased competition for light because isolated trees intercept more radiation in proportion to trees in a row. But scattered windbreaks poses or have some disadvantages. One special disadvantage is that the cultural operations are more difficult as trees become obstacles for the machinery. And also, there is a much higher cost of establishing isolated trees. Why? Because young trees have to be protected against wildlife or cattle. And protecting each tree separately is much more expensive than protecting a row of trees. Let's see some pictures of windbreaks. In this case, we are using a plastic mesh to protect flower crops in the Netherlands. You see, this here you have one windbreak, and then parallel to it, we have another windbreak. Here, the predominant wind direction coming from the sea is from west to east. Here, we see a cypress windbreak protecting an orange plantation in Cádiz. And here, we see the use of a plastic mesh to protect carrot crops in Chipiona. We can use sometimes perpendicular windbreaks to protect from different wind directions. And here we see a hurdle. This is made of dry canes, protecting horticultural crops in Almeria. This is a cypress windbreak protecting the fruit trees. Well, these are no longer fruit trees, but they used to be fruit trees in the old atrium of the University of Cordoba. This is another view of the same windbreak with cypress that is still existing in the IFAPA Agricultural Research Center.